You record what I'm doing? Okay, so you are welcome to your PHY 101, Elementary Mechanics, Heat and Properties of Matter. In the last class, I tried to take us to the beginning of mechanics, how to show what motion is and how it could be specified. All right. And the idea there is for you to be able to know some of the terms I'm going to use. But in any case, I'm quite confident that most of us have done school certificate physics, and we are familiar with such terms as I'm going to use, such as the kinetic energy, thermal energy, specific capacity, and sundry other terms that I expect you to be able to, or to be familiar with. From time to time, if there is need, okay, from time to time, if there's need, I will try as much as possible to review some of these concepts so that I can concentrate on the content of your course material and be able to finish it on record time before it is time for your examination. But even before this, I think I should unmute all of you and try to find out maybe at the end of this class, I can go ahead and ask that. For now, I think I will just make do with the script first, and at the end of it, we can do a discussion on other matters that have to do with the administration of the class, your TMS, and all sorts of things. All right. So once again, you are welcome. Now, in the last unit, we examined how temperature is measured. Okay. So perhaps I should take us back to that quickly. Let me see if I can take you to that script. Let me take you to that script for the benefit of those of you that were not in that class, and possibly you were you have not we have not really started yet, because then the number was relatively low. So I will just quickly go through the essential parts. Okay. All right. So let me share that part first and quickly run through it. So I think this is the one. Okay. So we define temperature, or we said that temperature is related to the sensation of hotness or coolness of the body, the way we feel it. That sensation, it means we, if we are going to rely on on our sense organs, okay? But like I did say, such descriptions are usually subjective and cannot be used for scientific purposes. So for scientific purposes, we have to have a way of expressing our observations in terms of numbers. And that means measurements must be made. And I went ahead and described to us what we mean by measurement in the last class, and units of measurement. So let me quickly, based on that, carry you through what we have said. So we said that, well, the sensation of hotness or coolness is related with the average thermal velocity, or if you like, average thermal energy or kinetic energy of the constituent particles of the system. That's what I said. That is, when a body becomes hotter, the molecules or atoms or whatever particles or subatomic particles that constitute such a system will move much faster. That's what we said. Okay, so the hotter the object, the faster would the constituent particles move at the microscopic level. Now, measurement of temperature, we said, is called thermometry. I have warned that I don't want people to be defacing the script. Perhaps I will not be sharing my scripts with you anymore, since you are stubborn I will not share these scripts, and then I will just talk, and then you go and read your course material. Maybe that will pay off. Okay, because I don't think that in a class where I'm talking to adults, you can be that, you know, well, let me not use harsh words. It's not a fair deal at all. So if you make any more marks on this script, I may be forced to switch off this script and read it directly from whatever or wherever else. I'm just writing these things as a means of highlighting the key things that you must note. You will notice that I put them in boxes, the way the course material of an ODL system is supposed to be done. Do you understand that? So that is because your course material has not done that. Until we have reviewed the course material, you may not have it in that form. So, but sharing these now, I don't know, because I think I've tried to, let me even see from the security, why you should be sharing. All right, so, okay, I think there's something I have to remove here. You cannot annotate my content in any way. All right, so please don't make marks. I will switch you off. That's what I'm saying. I will switch off and just talk. All right, so now let us go back. I'm saying temperature is a measure of the average thermal velocity, average kinetic energy of the constituent particles. Constituent particles here refers to the molecules, the atoms, and sundry other particles that constitute a system. Measurement of temperature, we said, is called thermometry. All right? So the science of measurement of temperature is called thermometry. And any device used for measurement of temperature, you know as thermometer. You already know that. On the other hand, we said that heat can be defined to be, on the other hand, heat can be used to do different forms of work. So you already know that. We can, of course, you know that, how do I describe this now? Let me give an example that may be familiar to all of us. You know that a large part of the electricity used in this country, the electrical energy, if you like, used in this country is generated by burning fossil fuels, that is a natural gas, okay? So to generate heat. Now the heat may even, first of all, be used to heat water, all right, and generate steam, and the steam may then be used to run a turbine, as the case may be, all right? So you know that this is heat energy now being converted to energy of motion of the turbine, and the turbine now runs the circuits of electric motor, electric generator, I beg pardon, and then electricity is generated, okay? So that's why I did say that heat can be used to do different forms of work. And so it is a form of energy. So we define heat as the energy that flows from place to place or from body to body as a result of the temperature difference between them. All right. Now, we also mentioned, as it is in your course material, what is called the thermal equilibrium. We said heat flows from place to place or from one material to another as a result of the temperature difference between them. We've said that already. Now, when two bodies are in thermal contact, that is when they are in such a contact that heat flows from one to another, we say it is thermal contact. So when that happens, we will find out that heat will continue to flow from the hotter to the colder body until both of them reach the same temperature. Or if they are exposed to the surrounding or the environment, both of them will eventually reach the temperature of the surrounding or the atmospheric temperature. When this happens, the two bodies are said to be in thermal equilibrium. Now we discussed that. All right. Objects in thermal equilibrium do not exchange heat and have the same temperature. So look at that. That's why I'm putting this in this box so that you take note. When objects are in thermal equilibrium, there is no more heat exchange between them, and the temperature between the two parts will be the same. All right. Now, we also discussed what is called the zeroth law of thermodynamics. Now, I will not take you through the history of that. I believe that it is the first and the second laws had already been found before they realized that this was also an important one. And so it was suggested since this should precede the others, then they name it as zeroth law, okay, to place it ahead of the others. It states that if a body A is in thermal equilibrium with another body B, and B is in thermal equilibrium with another body C, then A and C are in thermal equilibrium. We have discussed that extensively. So measurement of temperature is based on this law. So take note. So can you explain why I'm saying that a measurement of temperature is based on the zeroth law of thermodynamics? So you have to try and take a look at that. I'll leave you to answer that because I think I'd explained that. So all you have to keep at the back of your mind to answer that is that now the thermometer is one of the bodies, okay? And then you are going to compare, all right? Its thermal equilibrium with the thermal, you are going to compare it with another body. So the heat that flows into it with the heat that flows into another body. So that will help you to answer that part of the question. Now, for any two bodies to be in thermal contact, the intervening medium, or what you call the partition or wall, must first permit the flow of heat through it. And we said this type of partition is called the diathermic partition or diathermic wall. Now, an adiabatic partition is one that does not allow flow of heat through it. We said that. So a process that occurs at constant heat as without exchange of heat can be referred to as adiabatic. An adiabatic process is one that occurs at constant heat amount of the system at constant heat. We also went ahead and discussed measurement of temperature and temperature scales, all right? And we said measurement of temperature is called thermometry, measurement of temperature. I want to believe, let me enlarge this so that you can see it wherever. Give me time to enlarge this script so that you can see it clearly. I want it to be much larger. Okay, I believe this is easily seen by everyone now. So I said measurement of temperature is called thermometry. Let me highlight that. Okay, that's the science of measurement of temperature is called thermometry. All right, take note of the terms that I've chosen or that we are using. Now, the instrument used is called thermometer. You already know that. Now, to measure temperature, a property of a substance or an object that varies linearly or directly proportional to the temperature is often used. Okay? Now, such a property is called the thermometric property. You know this from your school certificate physics. Can you give some examples of thermometric properties? I've given some of them here: volume, electrical resistance, emission spectra, as we are talking about the color emitted from heated object. Okay. Now, you will notice that nobody has been to the sun, but where we are sitting here, it is possible for scientists using some technology to be able to tell what the temperature at the core of the sun is. So how do they do that? They use this technique of what we call the emission spectra, the colors that are being emitted in the course of the processes that take place inside, all right, inside the core of the sun. So they are able to estimate, because of course these colors should be associated with some certain level of temperature. So to construct a temperature scale, two fixed reproducible points are required, namely the lower fixed point and the upper fixed point. The lower fixed point is defined as the temperature of the triple point of water the triple point of water, which is the temperature at which pure melting ice, liquid water, and water vapor go exist in equilibrium at normal atmospheric pressure. You see, even though most books will say temperature of pure melting ice, okay? The standard thing to say is that it's the temperature of the triple point of water. Because when ice is melting, of course, the liquid will be there, and part of it will already begin to evaporate, isn't it? any substance that exists in the liquid state will also have evaporation. Why? Because evaporation occurs at the surface. And I think when we get to that part, maybe I will discuss it again. Okay, because this is a consequence of the thermal motion. So some of the particles inside, that are knocking themselves on the ones that are close to the surface might knock them in the direction that they move off the surface of the liquid. So therefore, at the temperature at which liquid exists, evaporation also will occur. All right. So if you have ice melting and then liquid, and then you also have vapor, these temperature should be referred to as the triple point. Okay. So that is why I chose that. So take note of that. So that is the lower temperature, beg your pardon, what we call the lower fixed point. All right. Now, how about the other part? The other part is called the upper fixed point, and it is a temperature of steam at normal atmospheric pressure. All these things are known to you. The length interval between the lower and the upper fixed point you call the fundamental interval. You know that. So let me embolden some of the things I've used here. I've used two things here. The lower fixed point, take note of these, and then this is called the upper fixed point with the definition as given. So the interval, the length interval between the lower and the upper fixed point is called the fundamental interval. Now, the temperature scale is usually obtained by dividing the fundamental interval into a number of equal parts. Okay. Now, in the Celsius scale, you know that this is divided into 100, and you have other ones like the Fahrenheit. I think is the you can find out that out. I think the lower fixed point is 32, if I recall that. I will check that. I'm not quite sure of what I want to say there. So, but then the key point here is that the fundamental interval is divided into a number of equal parts. So that gives you the temperature scale. So once you have the temperature scale, then you can make measurements by comparing the variation in length, like as of, for instance, the length of mercury column, you can compare that, okay, with what other length of the fundamental interval that you want, that you have or you want to determine. All right. Now, can you name? So I said the temperature scale is obtained by dividing the fundamental interval into a number of equal parts. Accordingly, we have sundry temperature scales, so many of them. I have mentioned the Celsius scale, the Fahrenheit scale. We have what is called, another one is called, I think, the Remo scale, and the Rankine scale. I think I've heard that before, so you may bother yourself. But the most common one that we use in the laboratory is the Celsius scale, okay? All right, so the most commonly used in our laboratory here is the degree Celsius. So in the Celsius scale, the lower fixed point is 0 degrees Celsius, while the upper fixed point is the 100 degrees Celsius. This is known, but which of the many scales should we adopt? That's the question we should ask. Which of them, now that we have so many of them, I've mentioned about 3 or 4 of them now, which is the one that we should adopt now for scientific purposes? Which one of them should be very suitable? And for what reason should it be chosen? Here is the question again. You have so many temperature scales: Fahrenheit, Celsius, Kelvin, Rankine, Remo, and all that. Which of them should we choose? And what is the reason for choosing such a scale to be the standard scale for scientific purposes? But well, you may have an idea of this, right? First, you have to remember that we have defined temperature as a measure of the average kinetic energy, or if you like, how fast the constituent particles are moving. The average kinetic energy of the constituent particles of a system. That is, the hotter the body, the faster these particles move. So this suggests that there should be a temperature at which, at least theoretically, thermal motion should cease. So if we continue to go down and down and down, continue to reduce the temperature down and down, eventually, I think the motion should stop, at least theoretically, and within the range that is permissible by quantum mechanics. Those of us that will study physics will come to terms with this. Perhaps I should stop and even find out whether I am audible and you can see the screen. I would have preferred leaving it like this, but I'm not sure, so I should ask. I hope you are seeing the screen.
Yes, sir, we can see it.
Yes,
Can you also hear me very well?
Yes, sir. So you can see the screen.
Can see the screen.
All right. Very well then, so we can continue. So I did say that theoretically, we should have a temperature at which thermal motion should cease. This temperature is referred to as the absolute zero temperature. So you've heard that before. All right. Experiments have confirmed the existence of these. And I'm going to show you one of the such experiments, the results of such an experiment. Okay. The practical experiment that can confirm these is the variation of volume of an ideal gas with temperature, isn't it? If you do the plots of that, if you do the graph of that, it will give you something that looks like this, isn't it? So that's the volume in the vertical axis and the temperature, well, in the Kelvin scale. I will explain why we have chosen the Kelvin scale here, all right? And that is because this is the absolute temperature scale. So take note of that. So I said a practical experiment that confirms the variation is the volume of the variation of the volume of an ideal gas with temperature. And this is illustrated in the figure there. It is called the absolute zero temperature, all right? Or the, if you like, the absolute zero scale. And absolute temperature scale is 1, whose 0 point is absolute zero. That is 0. That's, of course, the temperature should be 0. And at that point, all thermal motion theoretically should cease. Now, mark the use of my emphasis on theoretically. Okay, that means there should be limits. Okay, beyond which we may not discuss. And I said this is imposed by the requirements of quantum mechanics. Those of you that will study quantum mechanics from above this level will be able to understand why we have put this right there. Now, the Kelvin scale is this absolute zero temperature scale, the Kelvin scale, okay? So, therefore, the SI standard of temperature is the Kelvin scale, of the Kelvin unit of temperature, written small Kelvin, beginning with small letter, but the unit is capital letter. Always when a unit of any quantity is named after someone or a personality, then the symbol, the first symbol has to be in capital letter, as it is here. As you can see, the absolute zero temperature in Kelvin scale is 0. So from this diagram, you can see it is 0. Look at it. The absolute zero temperature is actually 0 here. Now, the temperature of the triple point of water, that's pure melting ice, if you like, is going to be 273 Kelvin. And the temperature of steam at normal atmospheric pressure is going to be 373 Kelvin. All right, approximately that. So, but then you can see that I've also given the temperature in case this should be C. I think this is, let me see if I can. This should be the temperature T, anyway, in Celsius scale. So I want this to be in Celsius scale, all right, in degrees Celsius. So this is the temperature in degrees Celsius, as I put here in the bracket here. So at the absolute zero temperature, we have that on the Celsius scale as minus 273.15, minus 273 degrees Celsius. All right, 0 at the triple point and 100. All right, so take note of that. All these are known anyway. So so as you can see, the absolute zero temperature in the Kelvin scale is 0. At this temperature, the volume of this ideal gas should theoretically shrink to 0. Okay, so the corresponding temperature in Celsius scale, as I pointed out, is minus 273 degrees Celsius. The melting and the boiling points of pure water at standard atmospheric pressure are 273 and 373 respectively. Note that temperature difference in the two scales is the same. I think this is an important point. Let me put this in red. So I have done an equation to highlight that. We are using two different scales, but the change in temperature will be the same. Let's look at this diagram. You can see from this point to this point, from these 0.0 point of absolute temperature in the Kelvin scale, all right, to the temperature of the triple point here, the temperature at triple point is 273. So now in the Celsius scale, 0 minus 273.273 here will also give us 273. So now look at this one. 373 minus 273 will give 100. This one is 100 minus 0 will also give 100. So that's why I'm writing that delta T sub C is equal to delta T sub K. That is, the change in temperature on the Celsius scale is also equal to the change in temperature on the Kelvin scale. By extension, the temperature difference in any two temperature scales must be the same. Must be the same. All right. This is the basis for the conversion between temperature scales. And you know about this, and I've given an example. I even gave something that I expected you to have worked out. The length, for instance, of the mercury column. This one is taken from your course material. Okay, SAQ. So I've decided to work it out for you. The length of the mercury column of a mercury thermometer are 1.06 cm and 20.86 cm respectively at the standard fixed points. What is the temperature of a body? Of a body in degrees Celsius, which produces 7.0 cm of this mercury column. So you can find that, because if you have your course material, you can find it there. Now the solution. So let M represent the mercury and C the Celsius scales, respectively. Also, let the required temperature in the Celsius scale be small c, and this is illustrated in the figure. So I'm going to show you the figure now. Give me a minute to rule to that. All right, so it's here. So this is my mercury scale M. All right, so the scale, we are going to take measurements in cm here. This is the Celsius scale in degrees Celsius, like that. I have done a similar thing like this before. So you have the ice point, the steam point. So the ice point in the mercury scale is 1.06. Steam point is 20.86. And on the Celsius scale, 0 and 100. You already know that. Then midway, somewhere 7.0 cm, we have C, and we want to determine this C. All right. I want to believe you understand how this works out, having done it before. So the conversion temperature of the temperature scales will occur like this. So I'm going to have that the length, cut it, the ratio of this length to this length. Let me point that. Give me a minute to bring a pointer. From here to here, all over from here to here is the same thing as here to here, all over here to here. So you can see the reason why I'm writing 7.0 minus 1.06 all over 20.86 minus 1.06 is equal to C minus 0 over 100 minus 0. So we can rearrange that, isn't it, to get C equal to 5.94 all over 19.8 times 100 in degrees Celsius, which gives 30 degrees Celsius. I've given you one from your TMA in your course material to go and solve. Please try and do that. I think this is it. It's the same question, I believe. An ungraduated mercury thermometer attached to a millimeter scale reads 22.8 mm in ice and 242.0 mm in steam at a standard pressure. What will be the what will the millimeter read when the temperature is 20 degrees Celsius? So those are the things that we did in the last class. Having gone through this, perhaps I should stop before I continue to find out if you are at home with all of that. I believe you should have read through this by now. Is everybody at home with this now?
Yes, sir.
Have you been able to solve all the problems that you have that are related
Yes,
with
sir.
it? Very well then. All right, so now let
Yes.
us go to the next part.
Sir, can you please bring it down again from the diagram?
Now, this is something that we have already done. So, so now let me mute us and go on to the second part, and the next part of it.
So my hand is up now.
All right. In what we have just concluded, that's in the last unit, we examined how temperature, just a minute, let me choose a pointer. We examined how temperature is measured and the interconversion between various temperature scales. In this unit, we turn our attention to measurement of heat as a process, all right? Now, we have talked about measurement of temperature, and now we are talking about heat quantities and temperature quantities. So having shown how temperature can be measured, we also have to show how heat is measured. And I'm going to show you the physical meaning of what you have been doing, all the observations that you have been making in this respect. All right. So this process is called calorimetry. That's a measurement of temperature is calorimetry. I mean, of heat, I beg your pardon. Measurement of heat is achieved by a process called calorimetry. Okay. Now is taken from the word calorimeter, and it is not unrelated to the fact that the quantities of heat were initially measured in unit called calories. Biological scientists still use this, okay, calories. So when you are eating food, you'll be talking about how much calories are released by the food into your system to give you energy. So that is how this term evolved. Now, at the end of these units, you should be able to perform calculations on specific heat capacity and specific latent heat, or possibly specific heat capacity, and in particular method of mixtures. So maybe I'll break these part, latent heat separately, because okay, I think I can accommodate the two. So therefore, at the end of these, you should be able to carry out calculations involving specific heat capacity and specific latent heat, fusion, of vaporization, and all that. Okay, so we'll discuss everything associated with that. And then you should be familiar with what we call the method of mixtures. Okay, so those are the things that will be doing here. Now, heat and internal energy. Now, we have previously defined heat as a form of energy flow from place to place or from body to body as a result of temperature difference between them. Now, measurement of heat will ultimately depend on measurement of temperature, okay? Since we say that heat is a form of energy flow as a consequence of difference in temperature. So it means measurement of heat will have a lot to depend on measurement of temperature. So take note of that. But we have defined temperature in terms of thermal motion, right? We said it's the average, the measure of the average thermal velocity or average kinetic energy of the constituent particles, molecules, atoms, electrons, protons, whatever. The energy associated with various forms of mechanical energies due to thermal motion of the constituent particles of a system may be referred to as thermal energy or internal energy. Now, why? Internal energy, all right? Energy associated with thermal motion. But when motion occurs in a system, now realize that when they get too close to one another, they may exert a force of attraction depending on whether they are charged or not. So in other words, they may possess potential energy, and in addition, they have kinetic energy and other forms of energy due to that rotation, due to that spinning and all that. So the sum total of this kind of energy is what we call the internal energy. So in our discussion, we'll denote heat energy by Q and the internal energy by U as the need may arise. The SI unit of heat is joule. But those of you studying biological sciences, environmental sciences, and related sciences will most likely use the unit of energy called calorie, abbreviated as CL. This way, the conversion factor is given. 1 calorie is 4.184 joule. So we will be working, in case you find a question and then the units are given in calories or calories per degree Celsius and all that, whatever. So you should use this conversion factor and you'll get the same answer as somebody working with joules, all right? All right. Now, let us define what we mean by specific capacity for what is left of the time. Now, you know that energy is the capacity to do work. We know that. An object does work based on the fact that work is already stored up in it. Of course, you know that if you are hungry, you will not be unable to perform some certain task. That is, you don't have work stored in your system. You cannot cash much more than you have in your bank account. So it's the same concept. So the capacity to do work is, in proportion to how much, if you like, or must not exceed how much work is stored up in a system. So heat energy can be converted to other forms of energy and used to do mechanical work. I've already given an example of that, right? Of course, you know that mechanical energy too can be converted to heat, because you know that if the tire of a car runs over some time, it becomes hot because of the friction, the frictional force or the frictional force there doing some work, okay? When the car has to move from place to place, okay? So force times distance, okay? Is there work done, and this work is converted to heat. So you know that heat can be converted to mechanical work and vice versa. So mechanical work needed to produce the same effects as heat transferred is referred to as the mechanical equivalent of heat. Take note of that. So this can be done. Now let me show you how you can do that. For example, you can maybe put a stirrer, okay, in water or any other liquid, and then you stir, very briskly, and and you put the water in a calorimeter that's locked, very, very well insulated. Now you also put a thermometer there in order to see the temperature at the beginning of your experiment, and then you begin to stir. After some time, you come back and check the thermometer. You notice that the temperature may have risen, no matter how slightly. That means that the energy due to the motion of the stirrer has been converted to the energy of the heat energy as a consequence of the mechanical motion beg your pardon, the thermal motion, the increase in thermal motion, okay, of the molecules of water there. All right. So that is the kind of thing that you have to keep at the back of your mind. You see, I said earlier on that heat, as in one of my classes, that heat is a bulk property which results from, some motion of particles, of motion of molecules, atoms, or whatever, at the microscopic level, at the level that we cannot observe with our ordinary eyes. Okay, so those are the things we've said. Also, you know that the capacity to do work cannot exceed the amount of work stored up in a system. I've said that earlier. So you can ask, what are the factors that determine the amount of heat stored up in a system? What will determine? the amount of heat stored up in a system. All right. Well, for want of time, let me discuss this. The capacity to do work by converting heat energy will depend on the answer that we give to this question. In fact, to a very large extent, that's what we have to depend on the answer to this question in order to understand the physical principle involved in the storage of heat in a body. Well, based on our definition of energy, heat energy, let me write that, correct that, heat energy based on our definition of heat as energy flow due to temperature difference, it is clear that the amount of heat stored, the amount Q of heat stored, the amount Q of heat stored in a system of heat in a system will be directly proportional to the temperature difference. So in other words, the larger the temperature difference, the larger the amount of heat that is stored in that body or in that system. That's number one. Also, since thermal energy is due to mechanical energies of the constituent particles at the microscopic level, that is the sum total of all forms of mechanical energy, kinetic, energy of translation, of rotation, of speeding, then the potential energy, and so on and so forth. Okay? Now, it is obvious that the greater the number of particles in the in the system, the greater will be the amount of heat stored in the system. Because it is the more particles you have, the more of these. Having talked about the motion due to the increase in motion due to temperature, the next thing is if you have many more particles in a system, okay, than otherwise, then you should expect that it should have the capacity, right, to store more. Okay, that's another thing. So that's why I'm saying that since thermal energy is due to mechanical energies of the constituent particles at the microscopic level, it is obvious that the greater the number of particles, that is, the greater the mass of a body, the greater the amount of heat it is capable of storing. I think this should make sense. The more massive an object, okay, the more heat it is capable of storing. Let me give you an example of that. Now, when you are on your own, boil water, okay, to a certain temperature, probably boiling temperature, and then that's the water, put the water, let it be a large amount of water, and put a large part of it in a bucket full of it, and then take a little of it in a cup and put them side by side in the same surrounding, subject them to the same environmental condition, and go back maybe some 10 minutes or 20 or even 1 hour to check. Let me even ask, so that I think it's an experience all of us should have. So let me ask us. I want to be sure you understand the principle. So which one of them will run through?
The one that has larger water, the bigger bucket, we take time.
The one that will run through first. Is it the one in the bucket or the one in the cup?
The one in the cup, sir.
Any other opinion? Now, the person that answered that, the one in, you said, somebody said the one in the cup. Why? From what we have discussed.
It has
The one in the cup is evaporating fast.
Because it has what?
Let's have amount of liquid.
Please speak louder. I didn't hear you well.
It has lesser amount of liquid, sir.
Less amount of what? I'm not hearing you. Okay, I had to look. Okay, speak again.
It has lesser mass.
Okay, smaller mass, isn't it?
Yes, sir.
Yeah, it has a
Water in the
smaller
cup,
mass.
yes, is a smaller mass than the one in the bucket. So that's the idea there. So you can see I want to show you how the equation that we've been using evolved. All right. It's not enough to write the equations. The equations are not mathematical equations per se. They are physical equations that tell you real observations. So therefore, we owe you a responsibility to explain the physical content of every equation that you have written. Okay. So that's why I've taken the trouble to do this. Okay. So you have answered that rightly. So the water in the cup is less massive than the water in the bucket, and so both of them starting out at the same temperature, the water in the cup runs cold first, and then it will take much longer time for the water in the bucket to become cold. So this is the illustration. All right. So so next we have to realize that how much heat a body is capable of storing depends on the strength of the bonds between the particles. Yeah, I'm going to, it's 5. I'm through. I'm almost through. Next, we have to realize that how much heat a body is capable of storing depends on the strength of the bonds between the particles and the arrangement in any given phase. To that extent, the capacity of a body to store heat is a characteristic property of the system or body and varies from one substance to another. Okay? Now, let us summarize all of these in an equation. Okay? All these things that I've explained can be summarized. So by math, I mean, in terms of measurement, we can say that the amount of heat stored in a body is jointly proportional to its mass and the temperature difference, isn't it? So this, if we say Q is the heat, then it means we can write it as directly proportional to M times delta T, where delta T is the change in temperature, M is the mass, and C is the characteristic property, here that expresses how much heat is stored, and is called the specific capacity of the material. You have seen this before, and it should make no sense. So if we rearrange that equation, my C should be equal to Q over M delta T. So the SI unit of the specific capacity is joule per kilogram per Kelvin. And the table of specific capacity of some common substances could be found in any standard text and on page 38 of your course material. So you look for it. So I will solve one problem here and said how much heat is given off as 20 grams of water cools from 90 degrees to 30 degrees Celsius. So take C as 2,200 joule per kilogram per Kelvin. Now solution M is given. You convert it to kilogram, and C is given here. So my delta T, change in temperature, is the initial temperature 30. It cools, that's the initial temperature. The thing is cooling down, isn't it? It's 90, so it's cooling. Final temperature is 30. So you subtract 90 from 30 is minus 60. And then if you substitute all of that, we have minus 4.0 kilojoule that has been given off. That's 5.04 kilojoule is given off. The minus sign shows that the quantity of heat is given off, is not taken in. Take note of that. So then let me ask you to solve these problems as you are. So quickly copy this, and with that we've come to the end of this class to allow you to go to other classes, another class that you may be having at this moment. So you can screenshot that and try those questions out. So in the next class, I will begin by maybe trying out one of them. It's about conversion of heat, okay? Right, conversion of heat from one form to the other, or from other forms to heat, and so on and so forth. Thank you very much for your attention. You don't have any more time, so in the next class, we will go from here. All right, unfortunately, we don't have time. We don't have time, so I want to stop. So Okay, Dominic. Please send your question through. Okay, I'm going to open a discussion forum. So Olga Timothy, Joy Joy Amuche. Please, I'm going to open a discussion forum. Send all your questions through the discussion forum, since there is no more time. Okay. Thank you very much for your attention.
Thank you,
Good.
sir.
Thank you very much.